Hello, this is Graham. It's Monday the 12th of August and I'd like to talk about termites. First of all, we're going to have a very quick look at the original Langtons ant, which is in the entrance of the gallery. This was one of the first videos I did. This is the A, N and T matrix which get multiplied to give you ant. And remember that psi x of t really is space-time. This is what this is all about. It's about space-time and modelling the electron. And if you remember, this is the M file where we've got the 0 and 0 because we didn't want them included for this and this, because this is my energy equation that I play with. But for Langton's ant, we want that to be 0 and 0, which produces this. And so I've taken a copy of this and we're going to go and have a look at the termite code. So this is the Langton's ant code that we just saw, where I said I made a copy of it. And you can see you've got the A and the T, N and the T, which get multiplied to give you this. It's very similar to this. So this M file produces the termite, and you can see that this also has an A, N, and T. It's identical. So this exists on the Langton's ant lattice. It also uses the Langton's ant wave equation to do this. The only difference is that in Langton's ant we update the position of the ant and we also update the lattice all at the same time. So there's only two things going on within this loop. Okay, whereas on this one, which produces the termite, we have a new variable called new spin, which is injected into the equation. So we can't simply do a sum like we do in here, where we take the trace of the diagonal, or we sum it. And I'll explain that in a minute, why we can't do that. So what we have to do is we have to do it round robin. So we have to start with a theta and we have to update theta each iteration, which is why we're doing this. You can see that this is a fundamental theorem of calculus, where one would be h, and this would be your function x plus h minus function x all over h, which is the fundamental theorem, where h goes to the limit of 0. What we're doing is we're zooming in and we're saying that h is not the limit of 0, it's actually 1, and we're going to do an infinite number of iterations. So we can see that we're updating the new version of theta into the future, because we're at time step t, is going to be equal to the old theta plus half of this. And what this does is that new spin will be minus 1 or plus 1 as it oscillates. And by adding 1, it'll either turn it into 2 or 0. And by taking half of that, we're guaranteed either 0 or 1. That's what we're looking for. We're looking for 0 or 1. But then we do the normal ant, which is exactly the same as this ant here, including all of this. And then what we do is we say, well, we're going to have a current spin value at current time t is going to equal to the elements in the lattice. So this is the old lattice that hasn't been messed around with yet. So this is the lattice as it was originally initialized up here. What we do then is we then say that the new lattice that we're going to update at the current time t is going to be new spin. Now we've injected that because it's not available in the lattice. This has to come in externally to get things moving. Then what we do is we then update new spin. So we've just used it to update the lattice. Now we're going to update new spin using the old Kerr spin, which came from the lattice that was originally initialized up here. So side D is now updated, so we can't use that in here. So you can see there's a temporal sort of rolling shift in how we do things. And then once we've done that, because we're just basically oscillating Kerr spin, but Kerr spin is the element. So rather than inverting the element of the lattice straight away like we are with a normal Langton's ant, all happening in the same time index, look, t plus 1, t plus 1. What we're doing is not only are we using a different t plus 1 to the old t, but we're also using an old Kerr spin and a new spin. So this whole thing is all temporally shifted. You've got to be careful in which order you do all this. And what I wanted to do was I wanted to do the sum like we do here, where we take the trace of the diagonal. And that's what I did. I took the sum of it, and I didn't bother with this. I just took the sum. And I didn't get this. I didn't get the termite. So upon investigation of doing that, I created this variable which simply says, let's take the sum of psi d, which is what I would like to do, because that's what I'm doing in here. I'm taking the trace of the diagonalized of psi d. But at the same time, I'm going to take away all of the current spins that have been available, and I'm also going to take away all of the new spins, and this should be 0. And I've just stuck a little plus on there just so that it can shift the graph, because I wanted to find out why I wasn't getting the termite. And it's quite a very interesting reason why it doesn't work, and why you can only do the termite by doing it like this in a round robin fashion. You can't do it holistically like it is done in this one, where you're just taking the trace immediately and getting all the information you need in one go. But what I find interesting about this is that the termite doesn't look anything like Langton's ant. And you can see that it's got this sort of section where it's being repeated, and it's going in a curve, and I like to think of that as, because Langton's ant is modelling the electron, then maybe we can model how the double helix can create itself by attaching electric fields and magnetic fields in this kind of curving way as it curves in on itself. If this was proper molecules or long chain molecules, you would see that these would be a certain shape and they would vibrate in a certain fashion. And if you came to a point here where this had exactly the same matching pattern, then they would be connected to each other, or they would repel each other. And I like that idea. This for me is like proper cellular automata at the molecular level, whereas the cellular automata that I'm doing is very much at the atomic scale. And the reason why I'm showing you all of this is that we're going to move over and see some other work done by another chap, and we'll talk about it in the next video. But taking the statistics of this based on Langton's ant, we still get our little bell curve. Now remember, this bell curve is the S curve, which is this. So we're taking the spectra of the termite, just like we did for Langton's ant here, and we're differentiating that to give us this, I call it a bell curve. It's not a bell curve, is it? You know what I mean when I say bell curve. And when you take the second order moments from this one, you get this pattern here. And this is all very similar in its data, and its distribution of probabilities is the same as Langton's ant. It's really interesting. And that's purely because of the feedback system. This is quite an interesting one. Best way to understand this is to get to grips with that, and then find the bits that are different. And what you'll find is that it's actually straightforward. We're doing the ant and we're doing the lattice all at the same time, in the same timestamp in that loop. Whereas on this one, we've got a holding variable that holds the state of the lattice, and then that doesn't get used until much later on. And in the meantime, things are happening with the lattice that was before and after. So you can see there's it's like Towers of Hanoi. You're kind of using a holding buffer to keep variables. And I think that covers all of that. If we go back to the original mathematics, again, if anybody wants me to actually do the mathematics on this and show you how it all multiplies out, I will do a video on that. But leave a comment in one of the videos and I'll do that. Problem is I suffer from attention deficit squirrel, and I'll probably forget. Thank you very much for listening.